Hey! Welcome back to Innovative Creator. Astrophysics, the branch of science that seeks to understand the universe and the way it works, has long been interested in the mysterious concept of black holes. Black holes are regions in space with such immense gravitational pull that nothing, not even light, can escape from them. Their existence was first theorized through Einstein's theory of general relativity in the early 20th century, and over the years, extensive research and observations have reinforced their significance in our understanding of the cosmos. One of the tools researchers use to figure out the realities of space is the James Webb Space Telescope. While it wasn't actually meant to study black holes, since the focus is on the entirety of observable space, it's bound to pick up information about black holes too. But the problem is, the information it's picked up is the exact opposite of what we were expecting. Brian Greene has just confirmed the recent findings, and it turns out, according to the James Webb Space Telescope, black holes aren't real. Join us as we bring you all the details. Telescopic imagery from the Event Horizon Telescope of the black hole in M87 that rip on the fabric of space was the most direct evidence about this shocking discovery and how it's turned the world of science upside down. What are black holes? Black holes are cosmic entities predicted by Albert Einstein's theory of general relativity. According to this theory, massive objects deform the entire fabric of spacetime, creating what we perceive as gravity. When a star runs out of its nuclear fuel and undergoes a supernova explosion, its core collapses under the sheer force of gravity. If the remaining mass exceeds a critical limit known as the Chandrasekhar limit, the gravitational collapse becomes irreversible, leading to the formation of a black hole. But even with that, black holes have always been theorized about since their initial discovery. While black holes themselves can't be directly observed because of the way they're created, scientists have identified several key characteristics and properties through indirect observations. As light from background stars or galaxies passes near a black hole, its path is bent by the unmeasurable gravity, creating a gravitational lensing effect. While it sounds absolutely trippy, it's the only thing that allows astronomers to detect and study black holes indirectly by actually studying their gravitational influence on surrounding objects. So, what's around the black hole is very important here. When matter from nearby stars or gas clouds falls toward a black hole, it forms an accretion disk around the black hole. These vibrations created by the black hole rippling through the gas cloud are then picked up on Earth, massaged by a computer, and amplified by 57 octaves. The material in the disk becomes superheated and emits X-rays, providing another observable signature of black holes. The interaction of black holes with other massive objects can produce gravitational waves, ripples in spacetime, which were directly detected for the first time in 2015. So, there are both very old and new observations that have been made over time. Over the decades, extensive astronomical observations and advances in technology have provided quite compelling evidence supporting the existence of black holes. Gravitational lensing has offered a look into the distorted light from background objects, indicating the presence of massive objects with intense gravitational fields. Plus, X-ray emissions from accretion disks around invisible objects have matched theoretical predictions for black holes. Not only that, but the detection of gravitational waves specifically from the merger of black holes has provided direct confirmation of these powerful entities. The James Webb Space Telescope is a technological marvel that was created to revolutionize astrophysics, and it has not disappointed in its mission to uncover the secrets of the cosmos. As researchers eagerly wait for its data, they were not prepared for the astounding revelations it would bring. Armed with this state-of-the-art observatory, scientists went on a journey that led them to make extraordinary claims that challenged the very existence of black holes. Yes, researchers utilizing JWST data have reported intriguing phenomena that appear totally inconsistent with our traditional understanding of black holes. Some of these findings have pointed to the possibility of alternative explanations for the things we always thought were proof of black holes, and well, let's just say that the world of space exploration has done a complete 180. One of the problems has to do with gravitational lensing. With the JWST's advanced observational capabilities, researchers are expected to witness familiar gravitational lensing patterns that align with our understanding of black holes. The light should bend, and there should be that big black hole of nothingness that's causing light to distort, but some of the observed gravitational lensing events presented strange results. As you know, when matter falls toward a black hole and forms an accretion disk around it, the superheated material emits X-rays, which are detectable by telescopes. These X-ray emissions are among the key observable signatures used to identify black holes and study their properties. If the black hole is a certain size before a piece of matter falls in, after the matter falls in, the black hole gets a little bit bigger. The black hole's mass goes up by the amount of mass that falls in, but even that concept is being turned around on its head with the JWST. Scientists have scrutinized regions suspected to contain black holes, observing their X-ray emissions in greater detail. Unexpectedly, certain black hole candidates have shown peculiar patterns in their X-ray emissions that challenge the conventional understanding of these cosmic entities. The unexpected variations in X-ray brightness, spectral characteristics, or timing properties have left researchers wondering if traditional black hole models adequately account for these emissions. This uncertainty has given rise to alternative explanations that explore the possibility of other exotic compact objects or modified gravity theories. One of these has to do with gravastars. These hypothetical objects have captured the imagination of astrophysicists as they present a unique twist on the classic black hole theory. In the gravastar model, the exterior still appears similar to a black hole, following the well-known metric that describes gravity's behavior around such massive objects. However, a fascinating twist lies within its core. Instead of a single singularity like the one postulated in traditional black holes, gravastars have more of a de Sitter metric inside. What takes things even further is its event horizon, which hosts a thin shell of matter. This peculiar configuration sets gravastars apart from conventional black holes and prompts scientists to consider intriguing possibilities. The Laser Interferometer Gravitational Wave Observatory, LIGO, has also played a pivotal role in our overall journey to explore the cosmos. Detecting gravitational waves from distant cosmic collisions has allowed LIGO to provide valuable insights into the nature of compact objects. Plus, in some instances, the gravitational waves detected by LIGO have also exhibited characteristics that are completely indistinguishable from those of ordinary black holes. So, something is definitely going on here. In the realm of astrophysics and general relativity, the no-hair theorem has long stood as a prominent principle shaping our understanding of black holes. According to this theorem, all stationary black hole solutions to the Einstein-Maxwell equations, which describe the gravitational and electromagnetic forces, possess a unique set of characteristics. These specific attributes are the black hole's mass, angular momentum or spin, and electric charge, collectively referred to as the black hole's hair. The no-hair theorem suggests that any other distinguishing features of a black hole beyond its mass, spin, and charge are considered hair and are believed to be lost beyond the event horizon. This event horizon acts as an impenetrable boundary beyond which information is seemingly irretrievable from an external observer's perspective. So, to put it in one sentence, conventional black holes have been thought of as relatively simple and devoid of any further distinguishing properties. However, in a remarkable study, Stephen Hawking, Malcolm Perry, and Andrew Strominger challenged this traditional view of black holes. Their groundbreaking research presents the existence of what they call soft hair in black holes, suggesting a more complex structure than anyone previously thought. Soft hair refers to a collection of quantum properties that are thought to reside on the black hole's event horizon. Unlike conventional hair, soft hair is not associated with the black hole's mass, spin, or electric charge. Instead, it is believed to have subtle quantum properties that encode information about the black hole's interactions with its surrounding environment. The existence of soft hair would have profound implications for our understanding of black holes and the nature of information in the universe. It could potentially resolve long-standing questions related to the information paradox concerning what happens to the information of matter that falls into a black hole. The idea of soft hair hints at the possibility that black holes may retain subtle quantum fingerprints of their past interactions, raising the exciting prospect of retrieving information that was once thought lost beyond the event horizon. And if that's true, then what the James Webb Space Telescope found would be true too. But if you reel things back in time a little bit, this concept has actually been there for a really long time. Back in 1974, Stephen Hawking proposed a groundbreaking idea called Hawking radiation. According to this, black holes emit radiation over time, which causes them to lose mass and eventually disappear. At the time, though, this radiation seemed to be random and didn't carry any information about what fell into the black hole, which clashed with the principle of information preservation in quantum theory. Scientists did try to combine quantum theory with gravity to solve this paradox, but they ran into mathematical problems and couldn't make sense of it. The situation seemed quite confusing. This is probably why the theory didn't actually pick up and somewhat disappeared as the world of science went on. However, a recent study led by Netta Engelhardt and her team made exciting progress. They re-examined Hawking's formula and found a new calculation suggesting that information does escape black holes through their radiation after all. The revised formula proposes that the radiation carries subtle traces of the lost information inside the black holes. As the black holes evaporate, they emit this radiation, revealing some details about the matter that had fallen into them. This discovery is a significant step forward in understanding the information loss paradox and bridging the gap between quantum theory and gravity. At the same time, it flips the traditional theories of black holes completely. Both dark matter and dark energy are two mysterious components that make up a significant portion of the universe, yet their nature remains elusive. While black holes have long been considered the primary explanation for certain gravitational effects, there is growing interest in exploring how dark matter and dark energy might play a role in these cosmic phenomena. Dark matter is an invisible, non-interacting substance that exerts a gravitational pull, affecting the motion of galaxies and galaxy clusters. It is thought to be responsible for the observed gravitational effects that have traditionally been attributed to black holes. Some scientists propose that the dense concentrations of dark matter could create regions of immense gravitational influence, mimicking the gravitational pull typically associated with black holes when, in fact, it's just dark matter. Similarly, dark energy, which is believed to be responsible for the accelerated expansion of the universe, could also impact the gravitational behavior of cosmic structures. Although dark energy's effects are usually associated with large-scale phenomena, it won't be too much of a stretch to think that its influence on local gravitational interactions might also yield results similar to those traditionally linked to black holes. Exploring the roles of dark matter and dark energy in the formation and behavior of cosmic objects, such as galactic centers, might shed new light on our understanding of black hole phenomena. By investigating these alternative explanations, scientists aim to uncover more about the intricate interplay between gravity and the mysterious constituents of the cosmos. Another intriguing avenue of research involves alternative theories of gravity that challenge the traditional concept of black holes. In the realm of modified gravity theories, scientists propose adjustments to Einstein's theory of general relativity to explain gravitational phenomena without invoking the formation of black holes. These alternative theories posit that gravity may behave differently on cosmic scales, especially under extreme conditions. Instead of a complete gravitational collapse leading to a black hole singularity, modified gravity theories suggest that other outcomes are possible, such as a gravitational collapse stopping at a certain point. One prominent example of a modified gravity theory is modified Newtonian dynamics, MOND, which aims to account for observed galaxy rotation curves without the need for dark matter. Physicist Mordechai Milgrom proposed MOND in the early 1980s to explain what happens in space according to Newtonian gravity. The gravitational force experienced by objects within a galaxy decreases with distance from the center. Therefore, stars and other visible matter in galaxies should follow a specific pattern of orbital velocities as they move farther from the galactic center. However, observations reveal a different story. Instead of following the predicted pattern, the rotation curves of spiral galaxies indicate that the orbital velocities of stars remain roughly constant or even increase as one moves away from the galactic center. This unexpected behavior led to the hypothesis that galaxies contain a significant amount of unseen or dark matter that exerts an additional gravitational pull, explaining the strange rotation curves. In contrast to the dark matter hypothesis, MOND proposes a modification of Newton's laws of motion at low accelerations, particularly at extremely low accelerations characteristic of galaxy outskirts. Mond suggests that under these conditions, gravity behaves differently from what we typically observe on Earth or in our solar system. In Mond, the law of gravity is modified to include an additional acceleration term, which becomes significant in regions of extremely weak gravity. This modification effectively increases the gravitational force in low acceleration environments, leading to higher orbital velocities for stars at the outskirts of galaxies. Mond offers a plausible explanation for the observed constant or increasing rotation velocities in the galactic outskirts without requiring the presence of dark matter. It has been successful in explaining galactic rotation curves in various spiral galaxies without invoking dark matter and has provided a valuable alternative to traditional dark matter models for some gravitational phenomena, challenging the need for unseen matter in specific cosmic environments. But this isn't all there is to it. Emergent gravity, a theory proposed by physicist Eric Verland, also presents a unique perspective on the nature of gravity, challenging the conventional notion of it being a fundamental force. According to Verland's theory, gravity doesn't originate from some fundamental particle or field. Instead, it arises as an emergent phenomenon from the collective behavior of underlying microscopic building blocks. In the framework of emergent gravity, Verland suggests that gravity is not an independent force like electromagnetism or strong and weak nuclear forces. Instead, it emerges from the interactions of numerous elementary constituents that form the fabric of spacetime itself. Verland's idea builds upon the concept of holography, a fundamental principle in theoretical physics. Holography posits that the information describing a three-dimensional space can be encoded on its two-dimensional boundary. Verland proposes that gravity, traditionally thought to be a fundamental force that permeates the fabric of spacetime, emerges as a result of information processing on a holographic boundary. In Verland's theory of emergent gravity, the concept of entropy plays a central role. Entropy, a fundamental concept in thermodynamics, is often described as a measure of disorder or randomness in a physical system. It is also closely related to the amount of information contained in the system. Verland draws a profound connection between entropy and the perceived force of gravity. According to his proposal, when there is a redistribution of information within a system, there is a corresponding increase in entropy. This increase in entropy leads to the emergence of an apparent gravitational force, much like how gravity arises in the presence of mass in traditional physics. In Verland's emergent gravity, the force of gravity is connected to the redistribution of information, which is quantified by the change in entropy. As the microscopic constituents of the universe interact and exchange information on the holographic boundary, the information within the system changes, leading to changes in entropy. This change, in turn, gives rise to an apparent gravitational force on a larger scale, creating the perception of gravity that we experience in our everyday lives. The connection between entropy and gravity in Verland's theory is a fascinating departure from conventional notions of gravity as a fundamental force tied to mass. It opens up a new way of understanding how gravity may be intricately linked to the informational aspects of the universe. If gravity isn't quite the same as we'd always thought it was, then the entire basis of what makes a black hole what it is challenged too. But the problem here is, how could something so powerful be totally false? Is that even possible? Well, yes. Observing and studying black holes pose significant challenges due to their nature and the vast distances involved. Observational limitations have played a crucial role in shaping our understanding of black hole signatures, and at times, they may have led to misinterpretations. As discussed earlier, accretion disks are essential for understanding the behavior and properties of black holes. However, in the past, telescopes faced significant challenges when attempting to study these accretion disks in detail. Their limitations in resolution and sensitivity hindered a direct view of the accretion process near black holes. The accretion disks around black holes are typically relatively small and distant, making them difficult to observe with the precision required to grasp their intricate features. To overcome these limitations, scientists resorted to indirect measurements and studied the X-ray emissions from the accretion disks. Since X-rays are highly energetic and able to penetrate obscuring dust and gas, they provide valuable information about the presence and characteristics of the accretion process. However, relying solely on X-ray observations had its drawbacks. The lack of direct observations meant that some aspects of the accretion process and the black hole's properties remained unclear. For example, the exact structure and dynamics of the accretion disks, as well as the distribution of matter within them, were not fully recognizable from indirect measurements. As a result, misconceptions or incomplete understandings about the nature of the accretion process and the black hole's behavior may have emerged. Gravitational lensing offers exciting insights into the properties of black holes, but interpreting these observations accurately can be challenging, especially when multiple lensing effects overlap. In some cases, a single black hole can produce multiple lensing events, leading to complex and intricate distortions in the observed light. One of the difficulties lies in extracting the various lensing effects and attributing them to specific black holes or gravitational objects. Previous telescopes had limitations in their capabilities, such as resolution and sensitivity, which made it challenging to resolve and differentiate overlapping lensing phenomena. These limitations could have introduced errors in deducing the characteristics of black holes and the matter surrounding them. For instance, when studying the lensing of a distant quasar or galaxy, scientists may observe multiple images of the same background object due to gravitational lensing by intervening black holes or galaxy clusters. The positions, shapes, and brightness of these multiple images can provide valuable information about the lensing mass and the geometry of the gravitational field. However, disentangling the lensing contributions from various intervening objects demands precise and high-resolution observations. Black holes are frequently found in bustling cosmic neighborhoods, such as dense stellar clusters or at the centers of galaxies. These regions are bustling with various celestial objects, including stars, gas clouds, and other massive bodies. However, their crowded nature poses significant challenges for telescopes attempting to study black holes and precisely locate them. In the past, telescopes had limitations in their ability to resolve individual sources within these densely populated regions. The resolution of a telescope determines its capacity to differentiate closely spaced objects and discern fine details in their structure. In the context of crowded areas with numerous celestial bodies, telescopes might struggle to achieve the necessary resolution to clearly distinguish each individual source. As a result, identifying the presence and precise location of a black hole in these crowded regions could be arduous. The lack of adequate resolution might make it challenging to distinguish the black hole from its neighboring celestial objects, which can include massive stars, compact stellar remnants, or other massive entities. This ambiguity in identification could lead to uncertainty about the exact location of the black hole within the cluster or the galaxy's central region. Without clear resolution, telescopes may not be able to discern the unique characteristics of a black hole, such as its gravitational influence on nearby objects or the specific emission signatures from its accretion disk or surrounding gas. This limitation is a problem for a comprehensive understanding of the black hole's properties and behavior. Analyzing the spectra of black hole candidates is crucial for gaining insights into their properties and understanding their behavior. The spectral data obtained from black holes contain valuable information about the composition, position, temperature, velocity, and other essential characteristics of the surrounding matter and the black hole itself. However, obtaining high-quality spectral data from black holes can be challenging for several key reasons. Black holes often emit faint radiation, especially in certain wavelength ranges, making it difficult to detect and measure their spectra accurately. The faint emission can be overwhelmed by the brightness of nearby stars or other celestial objects, leading to challenges in isolating and analyzing the black hole's spectral signature. Because of the faint nature of black hole emission, telescopes often need to collect data over extended periods to accumulate enough photons for a meaningful spectrum. Longer exposure times may be necessary to improve the signal-to-noise ratio and obtain